Right, so when we draw pictures of lenses and mirrors, mirrors are going to reflect, lenses are going to refract, and sometimes reflect too, depends on the scenario, but mostly refract. So we're going to draw a bunch of diagrams, and there's key words that we need to understand. There's always going to be a center line that just passes right through the middle of the mirror, and we call that the principal axis. And usually it'll be drawn on the paper for you, but you could always draw it. It just goes through the middle of the mirror. And then on that principal axis, you're going to see a few things noted. And sometimes they're drawn for you. Sometimes you're going to have to measure them and draw them yourself. One of those is usually labeled with a capital C, and it is the center of curvature. Now, the reason they call it a center of curvature is these mirrors are called spherical mirrors. Not because they actually are full spheres, but if we continued them, we could continue this curvature as if it was a sphere. So we could make this mirror go around in a full circle. We don't usually, but we could. And so they call it the center of curvature, and they call these spherical mirrors because we could keep extending it around and they would make a circle. And the C is, if it was a full circle, that's where the center would be. Okay, so if we extended this mirror so that it made a complete circle, the center of curvature is where the center of that circle would be. That's what that term means. Now, for the lens or mirror, there's going to be a defined focal point. And the focal point we label with F, and that's the point that all the light rays are going to reflect through if they're parallel. If they're not parallel, we're still going to be able to draw some light rays reflecting through the focal point. So the focal point is actually that spot on the principal axis where all the light rays come through. Now down below you see a little f. The little f is for focal length. That's just how far is the focal point from the center of the mirror. And then you also see the big R down at the bottom. That's just for radius, and we don't usually use that word too much, but sometimes you'll see it labeled. Just imagining again, if this mirror actually did go all the way in a circle, that would be the radius of the circle. It's typically not as important as the focal length. So the center of curvature dot, the focal point dot, and the focal length distance, those are kind of the key features. And the center of curvature dot and the focal point dot, we always put on that principal axis that runs through the middle of the mirror. So those are your key terms that are new and going to help us draw some pictures today and in days to come about how these light rays reflect and refract through mirrors, off of mirrors and through lenses. All right. Everybody get what you need from here? Okay, we're going to focus today for a few minutes on mirrors. And if it's a concave spherical mirror, it just means that if we continued the curve, we could make a whole sphere out of it. If it's concave, it means you're facing the side of the mirror that's caved towards you.
Wait, how was her hand facing upwards when everything is reflected down?
Crazy, huh? So we're gonna practice here so you guys can see yourself, right?
Yeah.
Probably look upside down from your distance. Yep. So I'm gonna angle it over here, and what I want you to do, unfortunately if you're not in here you won't be able to do it, but what I want you to do is come over here where you're kind of off to the side and walk towards the mirror so you can see a reflection, and just watch what happens to your reflection as you get closer, and you'll be able to see yourself. Okay, so one at a time, go ahead, just take your little field trip.
I don't
going first? I'll go first.
It should be upside down,
Yeah.
getting closer and closer, and there's a point where.
Oh my gosh, my eyes. Whoa, that's weird. It's making my eyes water. Watch, you do it. You do it.
I don't like it. Okay, wait, where am I?
You like go out of. Did it
view
make your eyes
for a
water?
minute and then
Mhm. Yeah, it goes blurry and then all of a sudden.
it just hurts your eyes.
And we like so close.
Okay.
That's really cool. Rest of it on track, give it a shot. This is how you go from being upside down to right side up.
Oh, this hurts.
The taller you are, the harder it is with this setting. I need a bunch of tall people in this class, so. So Lauren had an interesting observation looking at the picture. She's like, wait, the hand is right side up, but the tree behind her is upside down. And so what you hopefully notice here is that when you're far away, you're upside down. But when you get close enough, you flip back around and then you're right side up. And so her hand was close enough to the mirror to be inside that distance where it's right side up. But as it moves away, you get past that focal point and curvature point, and you start seeing everything upside down. All right, so these concave mirrors, and you can see how this is sort of caved in, right? Like you can walk into the cave sort of thing. Okay, that's a concave mirror. So these are mirrors that can zoom in on a field of view if you get close enough. Okay, so these are the kind of mirrors that you might see, you know, when you're trying to do makeup or something. So it kind of zooms it in, but if you get too far away, then it eventually it's going to actually flip and it'll be upside down. So you have to have it close, but it's going to magnify a little bit. But even though it makes it look funny, like her hand looks really big and awkward, and the tree behind her is upside down, and still when we draw the pictures, the angle of incidence still equals the angle of reflection. Even though it looks funky and the mirror is curved, the angles are still equal, just like they were with a plane mirror. So that law of reflection still applies, okay? So when we draw it in, whatever the angle of incidence is, we draw a normal line, and then the angle of reflection is gonna be the same. It's just that the normal line keeps changing, right? At the bottom, the normal line's going like this, and then it's like this, and then it's like this, and then it's like this. So you have to be careful that you draw the normal line correctly. All right. Another term for these kind of mirrors is converging mirrors, because they, as you can see in the picture, they converge those rays into a nice spot, the focal point. And so if you get to that focal point, now you're going to be where it's a nice, crisp, clear picture. The focal length in concave mirrors is 1/2 the radius of curvature. So with this mirror, it's not very deep, right? So if we were going to make this a sphere, that would be a really big sphere, right? And so its focal point is halfway to the center of the circle. So if we made this a sphere, you know, that sphere, the halfway point's like probably here. So the focal point's going to be here. That's why you have to get pretty close before you actually see yourself face up. Okay. Kind of distracting. All right, so those are concave mirrors.
What about like the ones that are towards you? That like they use to spotting you at the store?
Yep, that's coming up next. Okay, everybody have what you need for this slide? Okay. So convex mirrors are the ones that bulge out towards you. So you're facing the bulging side, not the caved in side. And we have to draw extended rays for these because when the light rays come in, because the angle of incidence and angle of reflection have to be the same, we draw our normal line and it has to go that way and that way and that way. So these rays that are reflecting off are never going to hit each other. They're like spreading out. So in order to figure out where the image will be, we have to extend those rays backwards and see where they intersect. And what do you notice of the difference as you look at her appearance in the mirror and the background in the mirror? What do you notice is different here compared to before? Yeah, everything's right side up, not just her hand. And you can see a lot more, right? You can see a lot of the tree, you can see a lot of the sky, you can see more trees all around the edges. Kind of expands the field of view. It spreads those rays out so you can see more. So in a store, you don't want to see just one little part of the store, right? So if they curve the mirror, now they can see a broader view of the store being reflected. So they can make sure if shoplifters are messing around, they can see a bigger area. You may have seen these. I haven't seen them much here, but in California, but I have seen them in a few places that have mountains. Sometimes on sharp curves, you'll see mirrors. You guys have seen those? Mm-hmm. So I just maybe haven't seen the ones that are here yet, but so those mirrors actually give you kind of a view so you can see around both sides of that curve. And so those are this kind of mirror to give you that wide range of view. So let's go back real quick. We'll come back and forth.
It looks like it's in California.
So if you look here, notice that the field of view is really restricted because it's magnified. We only see the tree and a little bit of the wall and her hand. We don't see all that other stuff, right? And everything past the focal length is gone. And the hand looks so big because the focal point's actually in front of the mirror. So if you got close enough to this and saw your face looks giant, right? In this mirror, because it's actually projecting an image in front of the mirror, so it looks huge. But if you look at this one, notice how her hand looks to be basically the same size as it is in real life. And that's because it's actually an image behind the surface of the mirror is where her brain's imagining this. So it doesn't make it look closer. So it doesn't look bigger. It just looks about the same. And it looks about the same distance from the mirror as her hand is from the mirror, just behind. But you can see much more field of view. So for convex spherical mirrors, the center of curvature has to be behind, right? Because it's the center of the circle if we made it a whole sphere. And so the only way to make that mirror a sphere is if we go this way. So the center has to be behind it. And therefore the focal point has to be behind it as well. But still, just like all mirrors, whether it's concave, convex, flat, plane mirror, always angle of incidence equals the angle of reflection. So we can always use that same rule. That's what we call it, the law of reflection. It's not just like the suggestion, it's the law. When it comes in, it always reflects at the exact same angle. And it's been proven so many different ways that they're confident in calling it a scientific law. These are called diverging mirrors. So what was the other word for concave?
Converging.
Converging. So when things converge, they come together, right? And in a converging mirror, those rays all came together in a spot in front. These are diverging because all those reflected rays are like spreading out. They're divergent, but not like the movie. But still, another thing that's similar is the focal length is still half the radius of the curvature. It's just behind the mirror now instead of in front because the mirror curves away from you instead of toward you. So you can imagine in a fun house, if they want to make things look bigger or smaller, they can use concave or convex mirrors. They can do like mirrors that are wavy, so you get a mix of bigger and smaller, so your body looks all weird. Like they can just change the surface of those mirrors in a lot of different ways to create a lot of weird, mind-bending images.
Okay, back to the concave mirrors.
Yeah.
I'm just gonna get the last sentence.
Yep.
We're gonna go.
Alright.
Thank you.
All right, so I have another example of a converging mirror here. What do you see?
Oh, it's one of those things that makes it look interesting for the top.
Yeah, it looks like you can grab that blue hand, huh? See the blue hand?
Yeah, but it's. Oh, it's in there. Just break the middle out.
See the hand on top? Can you grab it?
Stop. That's tripping me out. It's a hologram. That's cool.
inside.
There's actually a hole.
Oh, interesting. You could really fool somebody with that. Like a
A
chocolate
little-
in there.
I should have put a cookie in there.
You should.
You gotta look at it back.
Is there a mirror
No,
on
go
the
away
this
from it.
side?
No, don't turn it.
Oh, sorry.
Yeah.
Sorry.
Yep.
Hey,
Well,
you
no.
make me hungry. You should like
This is
grab
the concave mirror. You can see the blue hand up on top. Looks like you can actually touch it, but it's actually down underneath. So it's like you can try to grab it, but there's nothing there. And if you look down inside, it's just,
Oh,
I need to clean it through dirt. So this is a concave mirror, and it's putting an image out in front. So it looks like there's something right there, but there really isn't. Now, the reason it kind of holograms is because this is also mirrored on the underneath. So you get a double reflection, which gives you that kind of 3D image to it. So that's a concave mirror sample. All right. Now let's talk a little bit about lenses. So lenses are transparent, whereas the mirrors reflect. Lenses are transparent, and they will create converging or diverging light depending on their design, okay? And they do that by refracting the light. So converging lenses are thicker in the middle, like this type. Hopefully you can see it. It's a little faint, but it's skinny at the top and wide in the middle. So a lens like that. And this is the kind of lens in your eye. It takes all those light rays coming in and converges them into a focal point, hopefully on your retina. If it doesn't focus on your retina, then you have to get glasses to correct it so that it moves it to your retina. Diverging lenses are thinner in the middle, and so they're going to make the rays spread out. So they kind of look like that hourglass shape. They're wide at the top and skinny in the middle and wide at the bottom again.
So if my dog has like really cloudy eyes, does that mean like the lens is getting cloudy?
Mm-hmm. Yeah, ours is the same as, and that happens in humans too, but I think it happens in dogs more dramatically. And usually humans, when it starts to get to that point, it's called cataract, and so they'll just get the lens replaced with a just like a fake one. I said, I don't know what you call it, like a transplant, lens transplant, cataract surgery. Yeah, and it's weird for humans. It seems like it doesn't happen quite as dramatically as it does for some animals, and it also doesn't always happen equally. So like my dad's eyes, one of them never really had that problem, and the other one he had to have surgery and have the cataract removed, have the bad lens removed. So, and so it's kind of weird that it happened just in one eye for him. All right, so light bends at each surface of a lens, no matter which kind it is, whether it's converging or diverging, whether it's skinny in the middle or wide in the middle, the light bends at each surface. However, for thin lenses, we just show this bending only once. So instead of trying to show what we did when we were doing those refraction worksheets, where like we show it bending and then show it bending again, we just say it's simple enough to just show it bending in the middle of the lens one time instead of 2 times. But it actually does bend 2 times. We just simplify it, just draw an axis down through the middle of the lens and just draw it bending once at that center point.
I don't know if my dog is like the picture of health though. He also has like a tumor in his eye that's like this.
Yeah, I think our dog's got a lot of tumors too. She acts healthy, but when you pet her, you like feel these bumps under her skin all over. So the doctor tested a couple and said they're not cancerous. It's just benign tumors, but feels weird.
I think he's going deaf too.
Our dog's starting to bark and stuff a lot. I think she hears things and thinks she hears things, or so.
That's what my dog does. She went deaf.
Oh yeah. Our dog's about 12, and I think she's just, her sight's not as good, her hearing's not as good. It's just, yeah, she's getting grumpier. And so since we don't draw the light bending at both edges of the mirror, because they're usually pretty thin, it's not worth that little extra detail. When we measure the focal length, we know where the focal point is because we can see where the light all focuses in on. And so we measure from that point to the center of the lens. So that's our focal length. It's just from the center of the lens to the focal point where the light goes. And if it's a converging lens like the one on the top, all the light gets directed to that focal point. But if it's a diverging lens like the one on the bottom, then after it goes through the lens, it branches it all out. It makes those rays all spread out. So where you actually see the image is in front. So there's a term we're going to talk about, and I'll just mention it now because I think this diagram helps visualize it pretty well. Sometimes we see an image that is a real image. That doesn't mean it's a real object. It just means it's a real image. There's actually light rays passing through that point. And so this is creating a real image over here because these light rays are actually being bent and they actually do pass through that point. So if we see something here, it's what we call a real image. It isn't a real object, but it is what we call a real image. In this case, the rays that are actually traveling are going that way, but we see something back here. And so these are just extended lines we made, right? They're not actually light rays. So when it's these extended lines that tell us where we see it, that would be what we call a virtual image. It's not a real image. Now, neither one is a real object. They're just images. But this is, we call it a virtual image because there's actually no light rays intersecting there. It's just what our brain interprets. Here, there actually are light rays. And so if we use a magnifying glass, have you guys ever used a magnifying glass to like focus light and burn paper and stuff like that? what you're doing is you're putting the paper right at that length, right at the focal length. So all the light's focusing in on that spot. And so all the heat from that light starts building up and eventually you can burn something with it, okay? You can't really do it with this kind of a lens because it's spreading it out. It's gonna create a point on the other side. So you'd be getting a hot spot closer to you than actually where you're trying to burn something. All right, so that is converging and diverging lenses. So you picked up the parallel rays of light worksheet when you came in. If you didn't, go ahead and grab it now real quick. And I'm gonna have you guys work on that to draw those parallel rays, and depending on the kind of lens or mirror it is, you're gonna draw them through the focal point or extended line through the focal point based on what we covered in our notes, okay? So I can get the rulers. You don't really need protractors so much for this one because you don't have to measure the angles, but you probably will want rulers so you can, it's much easier to draw the straight lines and stuff so you can see the picture. So on this paper, you've got lines coming in. And so in the first, anytime it's a solid one, like this first example, that's a mirror. And anytime it's like a hollow space, that's a lens, okay? So for this mirror, these light rays are coming in, and what you're supposed to do is just continue them and then hit the ray and then go through the focal point. Hit the mirror and go through the focal point. So you're just gonna be drawing them as they reflect off this mirror and come back through the focal point, okay? And then for the lens, same thing, it's coming through. This is a converging lens, so it's gonna cause them to converge back through this focal point. Okay, just like we saw in our notes. And then for this one, this is the lights are coming from this way, so what kind of mirror is this compared to the light? Yeah, is it concave or convex here from the light? Convex. So these light rays are gonna actually bounce the other way. Actually, so you will need protractors so you can measure those angles. You can probably eyeball it, but if you want, I'll leave it up to you. If you wanna eyeball it or if you wanna actually try to measure it, you can. So it comes in, it's gonna bounce off at an equal angle, and then you need to extend the rays back through, because this is diverging when it reflects off this mirror. So then you're gonna have to extend the rays back through the focal point after you see them reflecting off, okay? And so it's just giving you some practice at trying to figure out, okay, is it converging or diverging? Is it gonna make the light come back to the focal point or away from like in front of the mirror, behind the mirror, in front of the lens, behind the lens? And so it just gives you kind of practice at drawing those out based on our notes. So that is your assignment. And like I said, you can, if you want to measure the angles precisely, you can. If you just want to eyeball it with a ruler, that's fine too. You'll get pretty good results.